In this video, we're going to focus on the hydrogenation reaction of alkenes. Our first example is going to be 2-butene. What do you think is going to happen if we mix it with, let's say, hydrogen gas? If you mix an alkene with hydrogen gas, and if you don't add anything else to it, under normal room temperature conditions, nothing's going to happen. This reaction is going to be, it's way too slow. In order for you to get a reaction with this alkene and hydrogen gas, you need to break the bond between the two hydrogen atoms. And that's very difficult to do. So we need a catalyst to speed up the reaction. One metal catalyst that we can use is platinum over a surface of carbon. When you put these two together, then the reaction will work. Hydrogen is going to add across the double bond. Now right now we have two hydrogen atoms across the double bond, but upon completion of this reaction, we're going to have 4 hydrogen atoms. As you can see, we've added 2 hydrogen atoms, and the double bond disappears. So we went from an alkene to an alkane. You can also write the final product like this. Here's another example. Let's say if we have a cycloalkene, particularly cyclohexene, and we're going to mix it with hydrogen gas, and this time we're going to use a different catalyst, palladium over carbon. So we know that the alkene will be reduced to an alkane. Whenever you add hydrogen to an organic compound, the reaction is a reduction reaction. If you were to remove hydrogen, it's known as an oxidation reaction. Now this reaction proceeds with syn addition, meaning that the hydrogens are on the same side. Now because you already have 2 hydrogens present, you really don't have to show the stereochemistry for this reaction. You can simply write cyclohexane. This is the answer. Now let's say if we have 1 hexene, and we're going to add hydrogen gas, and we're going to use nickel as the catalyst. This works too. The final product will simply be an alkane. All you need to do is get rid of the double bond. Now what type of catalyst is nickel in this reaction? Would you describe it as a homogeneous catalyst or a heterogeneous catalyst? Hydrogen is a gas, and most 6-carbon compounds are usually fluids, particularly this one, 1-hexene. So we could say that this is in a liquid state, and nickel is a solid. Whenever you have a catalyst that is in a different physical state than its reactants, what you have is a heterogeneous catalyst. Nickel doesn't dissolve in 1-hexene. And so because they're in a different phase, or in a different state, you have a heterogeneous catalyst. To have a homogeneous catalyst, the catalyst has to be in the same phase, or at least dissolve in a solution with the reactants as well. But that's not the case for nickel, so that's a heterogeneous catalyst. So what exactly is a catalyst? And how do catalysts speed up a reaction? Now, we're going to draw a generic reaction diagram. So in this potential energy diagram, we have the potential energy on the y-axis, the reaction coordinate on the x-axis. On the left, you have the energy of the reactants. On the right, the energy of the products. And at the top, the transition state or the activated complex. Now in this reaction, notice that the energy of the transition state is very high. To go from the reactant to the transition state, you need to overcome the activation energy, EA. That's the energy barrier. If you don't get past that hill, the reaction will not proceed. And so the higher the activation energy, the slower the reaction. So what a catalyst does is a catalyst provides an alternate pathway for the reaction. And by doing so, it lowers the activation energy. It makes it easier to go from the reactants to the products. So without the catalyst, the reaction is going to be very slow. But with the catalyst, it will proceed at a very high speed. It takes a long time to drive up the mountain. However, it takes a relatively shorter time to just go past a hill. So that's why it's very useful to use a catalyst to get an alkene to react with hydrogen gas. It speeds up the reaction greatly. Now let's go over another reaction. Let's say if we have 2-pentene, and if we mix it with hydrogen gas, and we're going to use platinum oxide, or platinum 4 oxide. This is known as the Adams catalyst. So if you see this on the test, basically it does the same thing as the other reactions. It converts the alkene into an alkane by adding hydrogen. Now sometimes you might see a problem like this. This is common. Imagine if we mix cyclohexene with deuterium, D2. And let's use palladium over carbon as the catalyst. How would you draw the products for this reaction? Be careful with this one. Feel free to pause the video and draw the product for this reaction. So we know that the double bond will disappear. D2 acts the same way as H2. Deuterium is the isotope of hydrogen. So chemically speaking, they react in a similar way. Now we said the reaction is syn addition. This time we have to show the deuterium atoms. In the case of hydrogen, we don't have to show it. If we had H2, we can simply write the answer as cyclohexane. But for this example, we can't do it that way. We need to show the deuterium atoms. And you need to show that the product that you're going to get is the cis isomer, and the regiochemistry of the reaction is syn addition. The two deuterium atoms, they add on the same side. Now you can also draw the product like this. Now here's a question for you. Are these two products identical, or are they like different? What would you say? Do we get one product or two products as the answer? It turns out that these two products are identical. They represent the same molecule. These compounds are known as meso compounds. If you haven't heard of that expression, you'll learn it soon enough. These molecules are the same due to the symmetry that's found in it. So even though both chiral centers have changed, they are the exact same molecule. So you only get one product for this particular reaction. Just keep this in mind. Meso compounds are identical compounds. But now let's talk about the mechanism of this reaction, exactly how it works. So how does the hydrogen molecule add itself across the double bond? Well, let's see. So imagine if this rectangular surface is the surface of the metal catalyst. And let's say this is the hydrogen molecule. As the hydrogen molecule approaches the metal, it binds with the metal. It is absorbed onto its surface. And as a result, the bond that connects the two hydrogen atoms breaks. And then eventually, the alkene will diffuse across the surface of the metal, where it's going to interact with the hydrogen atoms. Notice that the hydrogen atoms on the surface of the metal are in the form of atomic hydrogen. They're no longer molecular hydrogen. it's very difficult to break the bond between the two hydrogen atoms in the H2 molecule. But now that that bond is broken, atomic hydrogen is much more reactive than molecular hydrogen. And so this alkene reacts with the hydrogen, and these hydrogen atoms simply add itself directly across the alkene. Because both hydrogen atoms are facing towards the same side, that is towards the alkene, they're added on the same side with respect to each other. And that's why we get the syn addition product. For this particular reaction, you will never get the anti-addition product. The hydrogen atoms will always be on the same side with respect to each other.